My name is Frank McKenna. I'm here at UC Berkeley working for the Near East Sim Center. This is a short video on variable types and variable names that are available in C. Remember from first presentation, all data in program memory is stored as either a 0 or a 1. So the smallest unit of data, each of those individual 0, 1s in program memory, is actually called a bit. Now the trick programmers have used since programming began is to group bits together to represent more things, more data. So for example, the possibility of 3 bits, we have all those 8 possible combinations of those 3 bits. And with those 8 possible combinations, we could represent a whole number of things. We could, for example, represent 0 through 7. We could represent the letters A through H. Or we could represent any of the countries in the G8 group of countries. So C breaks program memory into byte-sized units, where each byte is equal to 8 bits. This is what I kind of show over here on the right. We have our program memory and we break it down into chunks of 8 size bits. Now to a single byte or a contiguous array of bytes, the programmer can associate the byte or bytes with a variable name and then use that variable name in the program to set and use the values stored at those bytes. And I'm going to just go through a couple of examples. So here we're creating a character. The variable name for that character is going to be A, and it's going to have the value assigned character 1. Now character 1, if you look up the ASCII text, is actually represented by this collection of bits. But as far as my program goes, the only thing stored at that byte is the character 1. Similarly, if I create a variable of type float, and it has a named theta, and I set that value of theta equal to 45, I would take up 4 bytes in memory, and those bits in those 4 bytes would represent the number 45. Similarly, if I create an array of floats, here's an array of 3 floats with those values set, that would take up 12 bytes in memory. Note that each of these bytes has a memory location, and that memory location can be obtained from the program, and those memory locations vary from 0 to the high address. The high address depends on whether it's a 64-bit or a 32-bit application. So let's talk about variable names in C. A variable is just a named memory location that can hold values and that you can use in your program. Now because C is strongly typed language, each variable must be associated with a type. When you declare a variable name, you also must specify the type of that variable. The size of the memory that's allocated when you create a variable, that depends on the variable type. And the variable names are actually made up of characters and digits. They are case sensitive, and the names must start with a character. An underscore counts as a character. You cannot start names with digits or funky characters. And also there's certain keywords that are reserved and they cannot be used as variable names. For completeness, I'm just showing those keywords that you cannot use as variable names. So now let's go over the basic types that are available in C, and we're going to start off with a character. Character is of size 1 byte, which gives you 2 to the 8 or 256 possibilities. The characters, they use the ASCII character set, which only uses 128 of those possibilities. And for example, if we're declaring a variable of type character, this is how we do it in a C program. Its character is the variable type, 1 is the name of the variable, and then we're going to assign it equal to the character 1. Remember, this is not the number 1, this is the character 1. Here we're assigning the character variable name, we're going to give it yes, and we're assigning it equal to the character uppercase Y. If we quickly looked at what 1 would be, here's that ASCII table in the background. Here's 1, there's the ASCII thing for 1, and there's the 8 bits that would actually exist in memory if we set that character. Next up we have integers. Integers take up 4 bytes, so there's 2 to the 32 possibilities for those 0s and 1s, and basically that means that any int can be in the range of negative 2 billion to positive 2 billion. An unsigned int, again, 4 bytes, and they're all positive, so the numbers can range from 0 to positive 4 billion. Here's how we define variable names of types ints and unsigned int, and we're setting them equal to have their values. So in C, and then like most other programs, a float is 4 bytes and a double is 8 bytes. And the representation of the zeros and ones follows the IEEE 754 format, where a certain number of bits are set aside for the mantissa, for the exponent, and then there's one bit set aside for the sign, indicating whether it's a positive or negative number. So with a float or a double, float is 32 bits, double 64 bits, we can have exponents 10 to the minus 38 to 10 to the positive 38 with a floating point number, and 10 to the minus 308 and 10 to the positive 308 with the double, which gives us, and the mantissa, basically the number of bits set aside for the mantissa, gives us approximately 7 decimal digits of accuracy for a float and 16 decimal digits for a double. And here's how we create a variable of type float. And in this case, we're using theta again over here. And here we create a variable of type double, calling it force. So just like in base 10, not all numbers can be represented in a limited set of bits. So just, for example, in base 10, we can't represent 1/3 in a finite set of digits. So there's a lot of numbers that cannot be represented in a finite set of digits in base 2. Here's a quick example. I'm showing 1.72 in base 10. This is one way of converting it to base 2. It's not the best way, but it just shows you what's going on. So if we're using 10-bit mantissa, this would be the 10-bit mantissa we'd set aside, and this is 1.72. This is our original number. If we convert our bits back, we get 1.719. So it's close, but it's just not exactly the number. So floats and doubles cannot represent all numbers exactly. What's the error in the possible numbers? It depends on the floating point value size, and this graph here just shows you the relationship between the precision and the floating point values. And a simple question, and one that you could play with using this approach, or you could Google online how to represent a number in IEEE, how to convert a number to IEEE. So the question is, can 0.1 be represented on a computer using IEEE? So we'll bring that up in the discussion tomorrow. So a variable that you've not seen before that exists in C is called a pointer. A pointer is 8 bytes if it's a 64-bit application or an x64 application, or it's 4 bytes if it's a 32-bit application. So pointer, you basically holds an address, a memory address. Remember previously I said that each variable has a memory address? Well, a pointer is a variable that can store what those memory addresses are. So here, for example, I'm creating a floating point type. I'm giving the variable named theta, and I'm setting its value equal to 45. So what's going to happen is the compiler is going to set aside some spot in memory for that variable, and that spot in memory, remember, it's going to have some location somewhere between 0 and the high address. So if we're saying that that memory location is this hexagonal number here, if I then have this line here in my C code where I'm creating a variable name called theta pointer, it's of type float pointer, so it's going to, theta pointer is a variable that points to a floating point, and then I'm going to assign it to have the address, the ampersand is the address of theta. In my C program, I would have this. I would have 8 bytes of data set aside, and those bytes would contain the hexagonal number equal to the address of that first byte of theta. So let's go over I have a little example in code pointer1.c, which will explain variables in a little bit more detail. So remember, a pointer variable is a named memory location that holds an address. So it's a variable that just holds the address of some other variable. Now to declare the pointer, you use the unary star. So in this line here, I'm declaring the variable pointer x, and I'm saying that it's a pointer to type integer. So this is how I do it. Variable pointer x is a pointer to an integer. And this is what the memory would look like if, these two lines of code. I'm creating a variable x, I'm assigning it equals to 10. I'm also declaring a variable y. I'm not setting it equals to anything. So initially it's just going to be whatever happens to be there, whatever 0 and 1s happen to be there. So we might as well just treat it as drivel. And then I'm creating the variable pointer x. It's an integer pointer, and I'm just assigning its value equal to 0. When you use pointers, So a little aside here, when you use pointers, always do an assignment and always set it equals to 0. Now, what we want to do, the unary ampersand gives the address of an object in memory. So what I'm doing here is I'm saying that the pointer x is equals to the address of x. So remember, x is that memory location given by this hexagonal number, and what this line is doing is just setting the variable to have that value. Now point 3, the unary star, anywhere else other than the declaration, treats the operand as an address, and then depending on which side of the operand, either sets the contents address or fetches the contents. What do I mean? So in this first line here, y equals star pointer x plus x, we are saying that we're going to set y equals to x plus star pointer x is whatever is at the address that x is pointing to. So this is, we're setting it equals to x plus whatever is at the address that x is pointing to, which is x. So we're going to get value y is going to be set equals to 20. So it's x plus whatever pointer x is pointing to. And now in the third line, we are going to set pointer x equals to 50. So star pointer x equals 50. So again, whatever x is pointing to, set it equal to 50. Okay, so this is what pointer x equals 50. Whatever x is pointing to, set it equal to 50. We're going to deal a lot with pointers today and tomorrow. So we're going to have to get used to them. It's the hardest part of C is understanding pointers. Bool is a 1 byte, can be true or false. And the thing about if you want to use bools is actually not, it wasn't in the original standard, therefore to include it, it's in any compiler that is C99 and above. To include a bool, to use bools, you have to hash include standard bool.h. So I'm going to go through some really quick examples of variables, usage in a program. We're going to create a program, var1.c. It's pretty much exactly the same as the hello world example we saw previously. The only difference is these 3 lines here. I'm declaring a variable, its name is a, and it's of type int. On this next line, I'm assigning a to have the value 1. And then in this line, the printf, instead of passing 1 argument now, I'm passing 2 arguments. The first one is a string with this %d. We've seen this in Python. So what the %d will do is in that function printf, it will take whatever that first argument is, put it in here, and print that out. This is variable 1.c. Slight difference in variable 2.c. I'm initializing the variable as I create it. So again, I'm creating a variable. Its name is a, and it's going to have the value 1. This program will print out exactly the same code. So the different variable types, this is how we print them out. We're defining an integer I1, a floating point number F1, a double D1, and a character C1. So the printf again, this time it doesn't take 2 arguments, it's taking 5 arguments. Again, the first one is this formatting string. We're telling it's print out int, %d, that %d stands for integer, %f float, %lf is a double, and %c is a character. The difference between this line and this line, and here I'm %e, I'm going to spit it out in scientific notation. And then the third line, like Peter showed when he was going through Python, we can specify the number of characters that are set aside, and then the number of significant digits that are printed when we use the scientific notation. So here we're going to use something that's 16 characters wide, 3 decimal digits. So up until now, we've only dealt with single floats, single characters, single doubles. We're engineers, we don't deal with things, we deal with vectors all the time. Vectors go in something called arrays. Now, an array in C is a collection of elements laid out in memory. It's a contiguous collection of elements. But the thing about it is, unlike Python, the elements have to all be the same type. So we have an array of doubles, an array of floats, an array of integers. We can't have a mixed array of floats and doubles and integers and floats and doubles or whatever. They all have to be the same type. This is how we declare it. We're declaring an integer array that's of size 5. It's going to have the name int array, and we're going to assign it. We're going to give it some initial values, 19, 12, 13, 14, and 50. Again, in memory, we're going to get an integer is 4 bytes. We're going to have 20 bytes in memory. Each of those bytes, each 4 bytes is one element of that array, and we access them using these square brackets. A0 is the first, and A4 is the last. Like Python, unlike MATLAB, indexing starts at 0. And this is just how we set the values. So int array 0 equals 21 would do this, which swap that value out to now be 21. And then if I was to print out the first or last, I'd see the 21 and the 50. And again, we use square brackets to access the values. It's multi-dimensional arrays. You can have n-dimensional arrays in C. It's not widely used because typically we're going to call Fortran routines to do our matrix operations. Now, the thing to know about when we're dealing with Fortran matrices, when we create a real array in Fortran, it's actually stored as an array, a single dimensional array, and those components are put in column major order. If we did the same thing in C, we would not get the same arrangement of those components, and it's called row major ordering. Now, because Fortran actually produces faster code for matrix operations, and a lot of the libraries that exist, the LAPACK, the MKLs, the BLAS, ScalaPACs, they all assume the matrices are in column major order. So it's very important when we're creating matrices in your C programs, you want to store them in column major ordering. So, a little thing here, I've talked about ints and unsigned integers and characters, but there are other qualifiers that we can put on those that change the values that can be associated with them. There's also something called the long double, which will give us up to 19 decimal places significant digits, and also if we need that larger values on the exponent, we can go to the plus or minus 4,932. I don't think we need that in civil engineering. They might need it in astrophysics or something. There are other types we haven't talked about, enumerated types. I haven't talked about void type. We'll see void tomorrow. And we also haven't talked about structures or unions. We briefly went into arrays, but we're going to go into arrays more in depth tomorrow when we start allocating arrays of unknown size. Okay, so that's it.